Lesson 10, Millikan's oil drop experiment. The elementary charge is the lowest amount of charge found in nature. It is the charge of the electron and the proton. The symbol we use for the elementary charge is small letter e. The value of the elementary charge is 1.6 times 10 to the negative 19 coulombs. The oil drop experiment was done in 1909 by Robert Millikan to discover the value of the elementary charge. The oil drop experiment had a setup in which two chambers were stacked on top of each other. A dropper bottle released oil droplets into the first chamber. In the first chamber, the oil droplets picked up small amount of charge, that is 1 or 2 or a couple electrons, due to friction in the chamber. The oil droplets fell into the second chamber, which contains an electric field due to parallel plates with an adjustable voltage. The oil droplets in the second chamber could be viewed by an observer through a microscope. There were 3 possible scenarios for the oil droplets viewed in the second chamber. All 3 oil droplets experienced the force of gravity pulling them down. This is why they dropped into the second chamber in the first place. But 3 different oil droplets might experience a different electrostatic force. In the first oil droplet I've drawn, the electrostatic force is greater than the force of gravity. This means that the oil droplet will experience an upward acceleration. In the second oil droplet I've drawn, the electrostatic force is less than the force of gravity, which means the acceleration experienced by the oil droplet is down. In the third, we have an electrostatic force equal to the force of gravity. This means that the oil drop will either be suspended or it'll be traveling with 0 acceleration or a constant velocity. The electrostatic force on the oil droplet is given by the amount of charge on the oil droplet multiplied by the electric field. Or, since electric field is equal to voltage divided by plate separation distance, the charge multiplied by the voltage over the plate separation distance. The gravitational force is the mass of the oil droplet multiplied by the gravitational field strength, little g. To calculate the charge on the oil droplet, we use F net equals the electrostatic force plus the gravitational force, where the electrostatic force is the charge times the electric field, the gravitational force is mg, and F net is ma. We can rearrange this for Q. Q is equal to ma minus mg divided by the electric field. For example, the mass of each oil droplet is 9.8 times 10 to the minus 16 kilograms. What is the charge on each oil droplet? We'll start this problem by determining the electric field between the plates. The electric field is equal to the voltage divided by the plate separation distance. The voltage is 40 volts. The plate separation distance is 0.2 centimeters, which is 0.002 meters. So the electric field is equal to 40 divided by 0.002, which gives us an electric field equal to 20,000 newtons per coulomb. We'll start by looking at oil droplet A first. The charge on the oil droplet is equal to Ma minus Mg divided by electric field. This is the mass of the oil droplet, which is 9.8 times 10 to the minus 16, multiplied by the acceleration of the oil droplet. Since the oil droplet is accelerating downwards, the acceleration is negative 3.3 meters per second squared, minus the force of gravity, which is again mass, which is 9.8 times 10 to the minus 16, times negative 9.81. Make sure you put the negative in for the negative 9.81 because the acceleration due to gravity is down. This is all divided by the electric field strength, which is 20,000, which gives us a Q equal to 3.1899 times 10 to the negative 19 coulombs. We can determine exactly how many electrons are on this oil droplet. If you divide the charge of the oil droplet by the elementary charge, you get 3.1899 times 10 to the minus 19 divided by what we know to be the elementary charge, which is 1.6 times 10 to the negative 19. This equals 2, which means that we have 2 electrons on oil droplet A. Oil droplet B is accelerating upwards. We assume because it's accelerating upwards that the electrostatic force on droplet B is greater than the force of gravity. We can find the charge on B by using Ma minus Mg divided by the electric field strength. Again, this is the mass of the oil droplet times the acceleration, which is upwards this time, so we use a positive value, minus Mg, which is 9.8 times 10 to the minus 16, times G, which is negative because the acceleration due to gravity is still down, divided by the electric field, which gives us a Q equal to 1.26 times 10 to the negative 18 coulombs. To determine how many electrons are in droplet B, we divide this charge by the elementary charge. This gives us 8 electrons. Oil droplet C is not accelerating. It has an acceleration of 0 meters per second squared. This doesn't mean it's not moving. It could have a constant velocity, or could be just suspended in the second chamber. The charge on oil droplet C is equal to Ma minus Mg divided by the electric field. Since A is equal to 0, the first term goes away, and it's just negative Mg divided by electric field. So it's negative 9.8 times 10 to the minus 16 times negative 9.81 divided by the electric field, which is 20,000, which gives us a charge equal to 4.8 times 10 to the negative 19 coulombs. We can determine the amount of electrons on charge C by dividing Q by the elementary charge, so it's 4.8 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19, which gives us 3. So there's 3 electrons on oil droplet C. Millikan analyzed the data from hundreds of oil drops to determine the charge in each case. He grouped the data into similar amounts and determined that each group was the multiple of the same number, the elementary charge, which was 1.6 times 10 to the negative 19 coulombs. And by doing this, he discovered the charge of the electron.